This one is C9H9O Cl. This would have 5 double bond equivalents. We have an aromatic ring 7 to 8, 6 C6H5, so 5H. We have 2 CH2 groups, and if we look here we can see what's left over. We've got a C, an O, a double bond equivalent, and a Cl. So we have a C double bond O, and we have a chlorine. So that should be all the pieces. Everything's counted down to 0. And we can put this together. We know the aromatic ring's going here. The CH2 groups are going to have to be next to each other. Now the reason we know this is because this CH2 group has 3 peaks, meaning it must be next to something that has 2 hydrogens, probably CH2. And this one is likewise. It's CH2, it's got 3 peaks, so it must be next to a CH2 as well. Now the two possibilities that we could come up with here would have the C double bond O here and the Cl here. Or the other possibility would be that the CH2 groups were connected here, and C double bond O is here and the Cl is here. Now this is the one I would be betting on, and the reason is, if we look at the way that certain groups interact with aromatic rings, we can see that a C double bond O attached to the aromatic ring will split it into 2 peaks, and those 2 peaks will be centered at around 7.5 ppm. An alkyl group attached to the aromatic ring, on the other hand, will usually result in a single grouping of peaks between 7 and 7.5 ppm. And that's exactly what we're looking at here. So there is no splitting of the peaks like we would see if the C double bond O was connected to the aromatic ring. That leaves me with this structure over here.